Our guest lecturer is live from Canada. So this is our first ChemSem. We're going global. We're going international. We're crossing the border. So our speaker today is Professor Graham Gagnon, and he's from Dalhousie University in Halifax, Nova Scotia, Canada. Any Canadians here in the audience? One Canadian, where are you from? From Canada, okay. That's all right. They'll still own you. So our speaker today is a full professor in the Department of Civil and Resource Engineering. And he got his training at the University of Guelph.
Guelph, yeah.
Guelph, okay. And then a PhD at University of Waterloo. He holds many different positions outside of the university as well. He is the director of the Center for Water Research Studies. And this is a big deal up there in Canada. It's a focal point for applied water research in Atlantic Canada. He has more than 120 peer-reviewed journal articles, over 250 conference proceedings, graduated over 50 students, and has been at his university now for about 17, 18 years. And he was recently, 2013, awarded an award, full award, for leadership in the water industry. So he's an expert in his field. It's great to have you here, our first international speaker. Thank you very much.
Okay. Well, thank you, Dr. Murray. I'm assuming the sound is all right. I'm gonna, I guess, go to share my screen here. And we'll get started. So I assume everyone can see this, all right? And I'll just go to my slide presentation. And we'll get started. So the body of work that I'm gonna talk about is understanding iron nanoparticles and lead occurrence in drinking water. And I've tried to make this relevant as I can to chemistry majors, and hopefully this will be relevant for your research and training ideas. So I had the opportunity to go on Andrews University Chemistry Department, see the type of presentations that were going on, and obviously I actually listened to a bit of Mark's presentation that he did earlier this year, and describing some of the issues in Flint, Michigan, and obviously quite a tragic story, and certainly I would encourage any student who hasn't heard Dr. Edwards' lecture to listen to it. But one of the issues that we had seen in particularly in Flint, but we'd seen in other cases when we've worked on lead projects, is this particular image that's shown here of sort of a brownish water associated with lead, which is not normally associated with lead discoloration, but from the standpoint of pure chemistry. But we know oftentimes that iron actually is associated with lead. And so we were really interested in learning a bit more about what are the interactions between iron and lead, and are they in fact somehow causal. And so really that image and a few other projects that we worked on really started to ask, we wanted to ask ourselves, how is lead being associated with iron in tap water? Why does this occur? And how can we prevent or mitigate or control this phenomenon if we can understand it at a research and scientific level? So that's going to be really the heart of today's talk, is just talking about the occurrence of lead and the occurrence of iron and why they are associated. So first and foremost, we have to kind of break down the problem with drinking water and how does water actually enter my property. And assuming we have some kind of centralized treatment, in the water industry, we would call this whole network a distribution system. And, you know, if you think about your own house and how water is entering into your house, if you're on a central or community system, you'd probably have what is referred to as a public water main out in the street. And then from the water main, water is going to enter into a service line, which is here, and then be connected to all the plumbing connections inside your house. And so let's sort of break this down a bit further. This is what water mains actually look like in Halifax. Halifax is a older city in Atlantic Canada. We're by plane about an hour north of Boston. So much like Boston and New York, settled hundreds of years ago, and we used cast iron pipe or unlined cast iron pipe as our water main material. This particular main probably has a diameter of about 100 millimeters or 4 inches, and the tuberculation that we see inside it is just these are just iron minerals, so goethite or magnetite, that form over time through a series of corrosion reactions. So this is obviously where our iron is coming from, because these are iron minerals. And then the service line, which I know Dr. Edwards did a lot of talking about with regards to lead. We have 2 different sides that are owned. So your water utility would own what is referred to the public side, and you as the homeowner or property owner would own the private side. Depending on the nature of your system, this might be completely a copper line, or it could be a lead line, or it could be copper and lead, some kind of combination of thereabouts. And then within your home, you have brass fixtures, and as well as soldering is used inside your home. Depending on the age of your home, it might be lead tin solder or some type of variation of lead-free solder. And so the point of all this is that lead can enter into your home through either fixtures, through the service line, or through solder. And certainly the greatest entry point would be through your service line. So to sort of break down the interactions between iron and lead, what I'm going to first do is do a bit of a lit review on projects. And there's been a number of projects like this that have really developed, I would say, a correlation or an observation that lead was occurring at the same time iron was occurring. And of course, doesn't necessarily mean causation. It just means that they were there at the same time. And so we wanted to try to understand this a bit more. And so to understand what the interactions will be, I'm going to draw upon this iron mineral throughout goethite and talk about iron mineralogy as we go, to make sure that we have a good understanding of what particles might be in our water system. So one of the first projects to sort of our research reports to draw this relationship between lead and iron was a project done at a university in Montreal, Canada. And what these researchers were doing was they found that particulate lead in RDT is random daytime sampling. So this is a particular technique to measure lead. So particulate lead through random daytime sampling was correlated with particulate iron. I'm just going to move this down here a bit. And what you can see is actually these were the 4 major factors that were correlated with particulate lead. But most importantly, particulate iron was the dominant factor of why we saw observed particulate lead. And it was interesting that dissolved lead, although significant from a model standpoint, was really not the same type of multiplier as, excuse me, go back here. Went back the wrong way, my apologies. As particulate iron. So one of the things we need to make sure when I was reviewing my notes for today is to make sure people understand how in metal and drinking water, how we distinguish particles and dissolved fraction. And it's really quite a crude method, in that we would use filter paper as our basis for distinguishing at a practical level in the water practice field, to distinguish what is dissolved lead and what is particulate lead. And we use filter paper that has a specific mesh size. We use 0.45 micrometers. So anything less than 450 nanometers or 0.45 micrometers is considered dissolved. Anything greater than 0.45 microns is considered particulate. So over the years, we've generally observed that dissolved lead is associated with perhaps changes in chemistry, reaction time, or just stagnation time of the water in the pipe, and of course temperature. Whereas particulate lead would also have these issues surrounding chemistry, but also have this variable of hydraulic perturbation, or some type water hammer or some type of high water velocity might get these particles off. And this particular image I'm showing here is just from this study, again from the group in Montreal, which looked at the aerators in different faucets and found the types of particles that we could imagine, lead particles that we were seeing in these faucets. And so again, to sort of think about what particulate and dissolved lead would look like, this is from work that we had a previous master's student, Megan Wazinski, did some work. And what she was trying to focus on was the impact of chemistry on lead release. What she was doing on this pipe here, so she had water being held in a series of pipes that were just regular premise plumbing. So this would be copper pipe, and the lead was through the joint, through a 50-50 lead tin solder. So water would go through here, we put lead tin solder, and then it would go down, and we'd hold water for 30 minutes and then measure the amount of lead. And so you can see we had different treatments, high chloramines, low chloramines. So high would be 3 milligrams per liter of chloramines, low would be 1 milligram per liter, and chlorine, or free chlorine, or hypochlorous acid in particular. And so free chlorine or hypochlorous acid is very common in the drinking water industry. And you can see what is happening is that this hypochlorous acid is oxidizing lead from lead 2 to lead 4, and in fact making it almost stay fixated on this pipe. Whereas when we change our disinfectant from chlorine to chloramines, in this particular experiment, we actually saw lead being released from the pipe and being dissolved or in a particulate form in the water matrix. And so why I've shown this slide after I listened to Dr. Edwards talk, and he was talking about what was happening in Washington. Of course, this was a key finding of his work in the Washington study, was this switch from chlorine to chloramines, and then the resulting lead being released into people's homes or into their drinking water. So this really starts to highlight the impacts of particularly chemistry on how chemistry can dictate lead release in people's homes. What Megan also did was not only hold water for 30 minutes, she held water for as long as 23 hours. And so you can ask yourself, why 30 minutes, why 23 hours, or some other longer period of time? Well, of course, all of us today are not at home. You're in a lecture hall, I'm in my office, and so water, if no one is at our homes, is presumably just sitting stagnated or allowing itself to react with the various pipe materials inside our home. Depending on how long that period is, we're allowing for a longer reaction time. So obviously it's clear from these data and from other types of literature that if we allow that reaction time to occur longer, we'll get a greater amount of lead release. And so in this case, we were getting, say, less than 100 when we had high chloramines to less than 1,000 micrograms per liter of lead coming out. So again, thinking about the holding times is going to be a key issue, a key consideration for how we would sample lead. And then for how we would treat our drinking water, this issue around the disinfectant choice that a water utility has between chloramines and chlorine would certainly contribute to the lead burden or the lead conversation that we would have to have. So to move along in our story then about understanding how iron and lead interact, I'm going to describe a project that we did here in Halifax, where we were looking at lead in people's homes. And so people and homeowners in Halifax were replacing their service line, and they were replacing, again, this piece of pipe that connects to the water main. And the utility was interested to know whether or not they could just have what we call a partial replacement and replace the public water supply, or have a full replacement and replace the full water supply. At this point, Halifax will only do full lead service lines because of the result of our work. And what we found was, in fact, that partial service lines won't do the job in Halifax. Full service line replacement will be the way to go. And that was a direct outcome of our research. But as part of this research project, people who were going through a service line replacement were asked if they could collect 4 1-liter samples. And so what would happen is the homeowner, prior to the service line being replaced, would collect water samples 1 liter at a time over 4 liters, and then finally a flush sample. They would then do this 3 days after their service line was replaced, 1 month after their service line replaced, 3 months and 6 months after their lead service line was replaced. And so one of the findings from this study, we found a number of things. First, as I mentioned, we found that in particular in Halifax, that partial service lines were ineffective at reducing homeowners' lead burden. And in fact, lead service lines, full lead service line replacement would be the only effective way in Halifax to deal with lowering the lead burden from a lead service line. But the other finding we found through this project was that in some areas of town, we would see higher lead concentrations consistently, regardless of whether they had a partial lead service line replacement or a full lead service line replacement. So let me walk you through what this graph means. So this pigged sample means that in the 1970s, the city of Halifax invested in a mechanical device, which is called a pigging device. And the pig would, essentially, this mechanical device would go through a cast iron water main and basically shear off these tubercles. What had happened, though, is that it really started to shear, in some respects, too much of this off, and it exposed a lot of the water main iron. And to this day, we get a slightly higher iron concentration in these neighborhoods. So what was done to mitigate this effect was to line the pig pipe with epoxy. And that has certainly dampened some of the iron in the people's homes. And then in other areas of town, the iron pipe was never pigged or mechanically cleaned. And then in other areas, they had ductile iron pipe, which is not cast iron pipe at all, which is a totally different way to manufacture iron pipe. So you can see in the areas where we did have the highest iron exposure, we also had the highest lead exposure. And then when we aggregated our data and we looked at the 3rd and 4th liter samples, and the reason why we looked at the 3rd and 4th liter samples is typically when we sample the 1st, 2nd, 3rd, 4th in that sequential manner, if you think about where your kitchen tap is and where water would go, how you'd get that 1st liter, you're probably still drawing water from inside your home. The 2nd liter is probably still drawing water from inside your home. It's really maybe the 3rd, 4th, and sometimes as the 5th or 6th liter where you're actually drawing water from the service line. And so we were interested particularly in the service line because that's where people would be replacing their pipe. And what we observed is that, and that indeed there was this sort of general relationship between higher lead concentrations and higher iron concentrations. Now, of course, this is on a log scale. I didn't really want to put a y equals x line through it to draw any type of deeper understanding, other to say that it appeared at a very general level that there was a relationship that we could see between lead and iron. So our third study that we saw this observation, we in fact did this project with Mark Edwards at Virginia Tech, where we were wanting to see the effects of the coagulant that we add to treat water and its impact on lead. And so for those who are unfamiliar with this term coagulant, we would typically use a chemical like aluminum sulfate, or it's by its trade name alum. And alum would be applied to lake water. And what essentially does is bring all of the small particles in the lake together to form what we call a flock. And then that flock is then filtered out during water treatment. So a water utility has a number of choices on which kind of coagulant they could use to form these flocks. So alum is probably one of the more popular ones in the water industry, and it's a sulfate-based product. The water industry can also use things like ferric chloride or polyaluminum chloride, and these are chloride-based salts. And really the issue around chloride and sulfate is an interaction in that we could interact with lead, which I'll explain in a bit. But again, just to make sure it's clear from an experimental design standpoint, what we were doing was adding these products into water, forming a flock, which is shown here, and then we would filter this flock through a 0.45 micron filter paper to basically simulate the physical chemical process of filtration. That filtered water would then be held in a piece of pipe like this, whether it's a lead pipe or a copper pipe. And then an electrical connection was then coupled to a copper wire, a copper pipe down here, so that we could have a galvanic cell, and that we'd be assured that lead would be leaching from this pipe, and we could then try to understand the impacts of the dissolved or leftover coagulant that isn't bound in this material. So what is the leftover coagulant of concern? Would either be sulfate or chloride, the anion that is present from this coagulant. And so this anion forms this ratio that is called a chloride to sulfate mass ratio. And typically, Dr. Edwards and a number of other researchers have published a lot of work around the issue around CSMR. And what they've shown is if you can get below a level of 0.5, you generally is going to be better for reducing lead leaching. Above 0.5, so higher chloride levels will lead to higher lead leaching. And this cartoon that from Dr. Edwards' group kind of highlights this, in that in our experimental design, we had a lead pipe connected to copper with a copper wire to allow electrons to flow. Our electrolyte is clearly going to be water. And so what is happening is then chloride's drawn to this anode. Lead is our anode in this galvanic series. And over time, what will form is lead chloride, and this is our dissolved lead. And so the theory being that the lead anode will eventually dissolve and lead chloride will come into our water solution. If we use sulfate, we tend to form a barrier around this, and we then tend not to have the same type of phenomenon. And in fact, lead sulfate as a salt will start to mineralize on top of the lead anode, and in effect reducing some of the impacts of the coagulant. So what we found, consistent with Dr. Edwards and other researchers, that indeed if you increase CSMR, so we've got two ratios here, one at 0.9 and one at 2, we will lead to higher lead release. But more importantly, what we found was a very strong observation in that if we had residual iron or residual aluminum in our sample, we would have a nice relationship with residual lead. This was a surprise from the standpoint that we didn't anticipate higher iron and higher aluminum leading to higher lead. So we were puzzled by this, but it certainly was consistent with some of the observations that we were making at the same time in Megan's work and some of the other observations that were coming out of projects from the University of Montreal. But of course, correlation does not mean causation. And so we wanted to develop an analytical method that would evaluate this at a colloidal level so we could understand these mechanisms better. And then once we developed this analytical method, we then wanted to apply it to drinking water and help us try to understand the mechanisms that are governing this relationship. So first, let me talk about some of the method that we developed. So this is what we did was we put a size exclusion chromatography. So for a chemist, this is a liquid chromatography system, and the column is gel permeation, or what I would call in the environmental field the size exclusion chromatography. We put this chromatography column in front of our detector, and our detector was ICP-MS, or inductively coupled plasma with mass spectroscopy. And so what is happening in a size exclusion chromatography system is water is flowing in this direction. The column is packed with gels that will basically allow larger colloids to elute first and smaller colloids to elute second in time. And then our detector will pick up these species. So if we typically use size exclusion chromatography with a UV detector, and this allows us to then characterize natural organic matter or many organic species and try to have an understanding of their molecular weight, or at least their relative molecular weight. And so this chromatogram first is showing where we would expect higher organic molecules or higher molecular weight organic molecules to appear, lower molecular weight molecules to appear in these peaks down here. And what this particular figure is also showing is that if we add goethite, this iron mineral that I talked to you about before, the organic material will start to bind with this goethite. And you can see in this particular case, this large organic that is present when goethite is not present is disappearing, which tells us that at 4.5 milligrams per liter of goethite, we're effectively binding the organic molecule. It's settling out of solution and it's no longer in our water matrix. So now if we apply this idea of size exclusion chromatography to our drinking water lead scenario, what we've decided to do is, and we published this paper earlier this year in Hazardous Materials, and what we showed is that first we could get a reliable peak when we sampled water from 23 homes in Halifax. We could get a consistent peak that would show typically around the 10th retention volume. So after 10 milliliters have passed, we would typically see this peak. The peak was reproducible with whatever profile liter we found. So whether it was the first liter that was sampled in the home, the second liter, the third, the fourth, and so on. So we knew that this peak was occurring at the same time. And the other interesting thing is that lead was occurring at the same time as iron, which, and why I'm saying is lead is occurring at the same time as iron is that if you look on the y-axis, iron by mass was about 100 times larger on average per sample than lead. So we know that there was more iron particles or more iron colloids in our sample than lead. And so we're going on the hypothesis that lead is being associated with iron. And the other interesting thing is the consistent size was about, I will say, somewhere between 10 and 20 nanometers. This particular line is shown here for a protein that we knew the molecular weight was around 669 kilodaltons, and the Stokes radius around 8.5 nanometers. So our peak is just slightly before it, so we'll maybe call it somewhere between 10 and 20 nanometers. So again, going back to this goethite iron mineral that I talked to you about earlier, this scale is 200 nanometers. So we can kind of measure this and look, it's probably about 2 millimeters, maybe 2.5 millimeters in this direction, and maybe 1 millimeter in this direction. So clearly much larger than these peaks. And in fact, if I did my best to measure this to scale, this would be about what 10 to 20 nanometers would be. Or we could look at it in another approach and to say this is a 10 nanometer scale, and these colloids are these iron colloids are 10 nanometers in diameter. So this gives you some idea of what a 10 nanometer particle would look like, and more importantly, this has a 100 nanometers bar. Again, this bar is 200 nanometers. So we multiply this bar by 2. You can kind of see how many 10 nanometer radii would fit. It's quite a number. So we get this sense that we have a high number of tiny 10 nanometer particles all throughout here. And then again, to give us some sense of what this would look like in practice at a cast iron water main, one can then realize that, this goethite molecule or goethite minerals that are formed here, there may be these little tiny nanoparticles that are moving through Brownian motion right above the surface or the interface between the solid and the water matrix that are then carried with advection and through Brownian motion into our tap water. And so how did we confirm that these particles were between 10 and 20 nanometers? What we did for each of these samples, we then would subsequently filter not only through 0.45, but 0.05 microns. And we observed that these particles were not being altered. They were consistently being observed with this size range, regardless of whether it was 100 nanometers or 50 nanometers. So we had fairly good confidence that this was the size range, and it was going to be in this sort of 10 to 20 nanometer size range. So then at a bigger scale, we could ask ourselves, well, do colloids really matter? And I'm going to try to get this up here. And how would they impact my drinking water sample? Remember before I showed you these pictures of what we do to define what dissolved lead is and what particulate lead is. And this would be particulate iron and dissolved iron too. We use a 0.45 micron filter paper. So this is our particle bar, which in the samples, the 23 samples that we collected in Halifax, would represent somewhere between 40 to 50% of our sample volume. So if we said it was, say, 45% of our sample, the other 60 or 55% would be considered dissolved. But in fact, that dissolved portion is really really two portions. It's a colloidal fraction and a dissolved fraction. And in fact, this colloidal fraction is much greater than what would be truly dissolved, or truly smaller than, in this case, 50 nanometers. And so what we're really observing is that these colloidal particles are truly contributing to our understanding of what is coming out in our sample. In other words, one can imagine then, if we go back to Michel's work at University of Montreal, this image, this bar is captured in this image. So we'd maybe have a few large particles contributing to our particulate fraction. But our colloidal fraction is really several hundred or even several thousand nanoparticles in this bar, contributing equally as much as our particulate. And our dissolved fraction is really quite small. And this is really then becomes important on how we want to think about managing these materials when we dose phosphate or other corrosion inhibitors for corrosion control. And so if we can understand that mechanism, then we can try to understand how we are appropriately removing or managing lead at the tap. And so in Halifax, much like many US cities, we would add phosphate to manage for corrosion control. And this little experiment that I've got shown here was an experiment where we used cast iron mains and we used PVC mains. And you can see that when we used PVC or plastic mains, we actually had no iron nanoparticles coming through our water system. Whereas when we used iron water mains, we then would see these iron nanoparticles coming through. And not only did we see iron nanoparticles, we saw 4 times the amount of iron or of lead particles coming out. We would still see PVC on our PVC water main through this lead pipe. We would still see a small fraction of lead colloids, but certainly it was increased when iron was there. And we confirmed that what was happening with these iron materials by doing a very simple experiment in that we use magnetite, and we've subsequently used this with goethite as well, as our iron mineral in this sort of simple galvanic cell. So we first in this galvanic cell did not put the cathode in water, and we had a small amount of lead released. After day 16, we put the cathode in water. Our current increased immediately, as did our lead concentration, and our lead slowly dissipated. And so our hypothesis is what's happening is that these iron minerals are settling on our lead pipe. These tiny iron minerals are settling on our lead pipe and forming a galvanic couple, which is then releasing lead into our water system. And then lead is associated with the other colloids that happen to be in water, whether they're iron-based or organic-based, as we saw in the PVC pipe scenario, which is then allowing lead to enter, lead particles, nanoparticles, enter into our home. And so when we've looked at iron corrosion and thought about how we could control iron corrosion, we would typically add phosphate. And this was from a PhD student that we had in our lab. When we add phosphate, we can see quite clearly that by adding phosphate, we can change our goethite molecule, our goethite particle. We can actually shrink it in half or make it much more dense and much smaller and allow it to settle in a much more effective manner. And we can confirm through dynamic light scattering that the iron suspension is in fact smaller. So this image is just showing, excuse me, how the iron mineral shrinks with increasing phosphate dose. So these samples have phosphate, these samples do not have phosphate, and so we would then end up with a much smaller particle and a much more manageable particle on our pipe system. And so then when we look at these data that were recently published, it begins to understand what's happening with phosphate and when we add it to our drinking water. So if we added 0.5 milligrams per liter of phosphate in our experimental system, we were getting concentrations that's sort of in the, for the PVC pipe in the 100 to 150 microgram per liter level. And in the cast iron main, we were getting maybe 200 to 300 micrograms per liter. Over time, by adding a consistent dose of 1 milligram per liter over a year period, we saw a very clear indication that lead was decreasing in the PVC pipe. So in other words, this smaller, these denser particles were being formed and being contained on the water pipe. And we saw this observation as well in the cast iron pipe. But of course, in the cast iron pipe, there's a little bit more sporadic nature because of the type of tuberculation that exists on these materials, and we probably need to extend this experimental time frame much longer for the cast iron scenario. So this particular idea of increasing dose from 0.5 milligrams per liter to 1 milligrams per liter has been implemented in Halifax. It was implemented last spring based on these data that we presented to the city. And in fact, over 1 year, these are full-scale samples from one home, the same home in Halifax. We sampled this home in 2015 when we were at a lower dose. And you can see already within actually a 6-month time frame, the impact of going from 1 milligram per liter to 0.5 milligrams per liter was being realized in this particular home. So the data here, total lead over in micrograms, is the additive lead through 13 sequential 1 liter samples. So to get the concentration, the average concentration, we would need to take this 70 and divide it by 13 to get our sort of quote unquote average concentration through that entire 13 sample sequential liter, or to just recognize this is the total lead mass over that sample volume. The other important issue you can see is that the water temperature is clearly having an effect. Depending on when we sampled the water, whether the water was 14 degrees Celsius or 22 degrees Celsius, would have an impact on the total lead being released from this particular home. But most importantly, the increase in dose is going to drive down our total lead burden. We will go back in 2017 and measure this home and see whether this lead burden is decreasing, not only because of the higher dose from 0.5 to 1, but over time as well. So with that, I'd again like to thank everyone at Andrews University to invite me to here and just give you a few summary thoughts of some of our analytical tools that help us develop an understanding of iron and lead interactions. And we, as I said, I think this is quite interesting that we're discovering these issues with nanoparticles. And it's certainly helping us understand how we can control lead in our distribution systems. If we think about the lead that's being released as a particle, a very tiny particle, as opposed to dissolved lead that is just reacting through chemistry. And I think there'll probably be more contribution in this work in this field as we understand what we are trying to deal with at a very practical level. So before I finish, I just want to acknowledge there's been a number of graduate student projects at Dalhousie that I've used, a number of PhD students that have helped. Ben Trueman, Safur, and Alicia were PhD students that contribute significantly to this work, as have some of the master's students that I cited. We have a number of project staff members that have helped us develop this work. We work very closely with our water utility here in Halifax. They've been very generous with their staff and their time collecting samples and trying to understand lead so that we can collectively reduce lead at people's homes in Halifax. As I mentioned, we work with Dr. Mark Edwards on one particular project, but he's been certainly very helpful to me in terms of understanding what is happening with lead in terms of at a much broader level, and just listening to his work and following his work in general. And also at Dalhousie, we've had a very strong materials team that's helped us develop some of our particular protocols. And so with that, I hand the mic back to Dr. Murray and welcome any questions from audience or anybody else happen to be there.
Hi, my name is Danielle, and I was wondering how effective basic household filters were in taking out the iron and lead particles. So I know a lot of students have Brita filter pitchers, and I was wondering if this was effective at all in regards to taking out the metal.
Yeah, that's a great question. That's something we're actually pursuing now because we're thinking about them as particles rather than just dissolved species. So the short answer is that when we've been testing that different filters over the last summer, and then trying to run it through our method, and what we found is that the pitchers or the household point of use systems that have a filter paper or a membrane. So there's various product names for these ones that not just have charcoal filters, but actually have a membrane. Those ones work. The ones with a charcoal filter, so the Brita ones, they're just charcoal based without, they haven't been too successful at removing lead. And again, these are the tests that we've been doing in Halifax, and obviously a lot of our water has had nanoparticles. And so we wouldn't necessarily think a granular activated carbon filter would remove a particle. They would remove a dissolved species. That's our hypothesis of why they're not necessarily effective. So the ones that with a membrane would be the ones that you would want to use.
Hi, my name is Victoria. My question is in regards to the graphs and the research that you showed us today in your PowerPoint. Were all these samples then taken from Canada?
Yeah, that's a great question, Victoria. Yes, they were all taken from Canada. And obviously, the method, so we work closely with colleagues in Canada. Obviously, our border is an interesting thing. Shipping samples across the border can be done, but sometimes it's a little difficult. So we tend to do most of our work in Canada, although we've done, as I mentioned, we've done projects with Mark and his group. We have shipped samples across the border, but typically we use our samples are from Canada.
Hello, my name is Dylan Zerman. My question was in regard to the use of phosphates. Are there any concerns with the phosphate interacting with other groups, like for instance forming a lead phosphate combination or some other? Yeah.
Good question, Dylan. So phosphate, I wasn't anticipating this question. I was anticipating a different question about phosphate. So I'll first try to answer your issue about phosphate. And you are absolutely right that the image that I showed of the iron material, clearly phosphate is being captured in this iron mineral. And I would expect for lead minerals, the same type of thing. Lead minerals would be containing phosphate and more than likely being deposited on the pipe surface and hopefully being stabilized on that pipe surface. So the question that I was anticipating about phosphate is sort of the broader environmental issue around phosphate and the use of phosphate in the water industry, and that if we discharge phosphate into the environment, we have other problems as a nutrient in lakes. And certainly the water industry is well aware of that problem, and why we spent a lot of time looking at the mechanisms is that if we could understand how phosphate's interacting, perhaps we could figure out a way to design a different chemical species that would be a bit more environmentally friendly to our lakes and our discharge areas.
Hi, my name is Dave, and in this area of the United States, a lot of water is withdrawn for private use from wells drilled on the land where the house is set for private housing. And there are pockets, at least in this area, that have a high iron and sulfur content in the water itself. Does that mean there should be some concern from the homeowner that perhaps if there's lead in the copper solder, in the copper pipe solder, that might increase the amount of leaching from that solder because in the water?
Good question, Dave. So first, couple issues. First is sulfate. Sulfate is actually going to be a bit of a friend for you in that sulfate, as I talked about with this chloride to sulfate mass ratio, sulfate acts perhaps not as aggressively as phosphate, but in a similar manner in that it's a bit of a mitigating factor on lead release. So having sulfate is actually going to be a bit of a favor for controlling lead. For iron, again, for a groundwater well, iron is going to be in a reduced form, meaning that it's likely to be dissolved. So dissolved iron is probably not going to have the same impact, and certainly I'd be surprised if it has the same impact that particulate iron is going to have, or iron minerals. Nevertheless, it is entirely possible that iron could form a reaction depending on the type of well that you have, whether you oxidize iron and form an iron particulate. Some systems will add oxygen or aeration. I've seen some homeowners do that, and of course then they will get iron particles forming. So it's really a question of what's happening with your groundwater well, and how is it still anaerobic or in a dissolved state when it in a reduced state when it comes out of your groundwater well and into your home.
My name is Michael. My question is, how do you go about choosing your disposal sites?
Michael, I'm not sure I understand your question. The disposal site in what sense? If you could just help me understand your question.
Like, how do you limit the environmental pollution? Like, what areas do you choose?
The environmental pollution from lead, or I'm not sure I understand. And so if you could just maybe expand what you're thinking, it would help me a lot.
Like, based on Dylan's question?
Yes?
About the phosphates and the water?
Okay.
Right.
Okay, thank you. Sorry about that. So when we add phosphate, and a lot of water utilities in the United States, Canada, and Europe will add phosphate as a way to control lead. Obviously, the first priority would be just to excavate a lead service line. Don't misunderstand me. That would be the top choice for any water utility. This, of course, has some construction costs and time lag associated with it. So phosphate has been found to be a very effective form to control lead. Phosphate's then dosed at a higher level, and so we have excess phosphate that would go into a wastewater treatment plant. So our wastewater treatment plants that would probably be run by the city is really our way of controlling excess phosphate that would be going through our drinking water system, through our toilets, and then ending up at our wastewater facilities. So we'd be controlling phosphate at our wastewater facilities. And really, as I said, the best way to control phosphate would be not to add it in the first place, but we would need to make sure all our lead service lines are replaced first before we could have that type of choice, or design a different type of corrosion control inhibitor to do that.
Hi, my name's Don. I was just wondering if you knew off the top of your head the number or percentage of service lines that are still made of lead or main lines.
Great. Yeah. So I should have cited that earlier in my talk, and I apologize for not doing that, Don. So there was a paper earlier this year in the Journal of the American Waterworks Association. I believe it was in the July or perhaps June issue of the Journal of American Waterworks, published by a man by the name of Steve I. And Steve, the estimate based on his calculations was somewhere around 6.1 million to as high as 10 million lead service lines exists in the United States. That would be the sort of current best estimate, somewhere between 6 and 10 million. And for the most part, those would be public service lines. More than likely are going to be in sort of the northeast, eastern part of America, sort of the older parts of the United States, if you will. In terms of water mains, we typically don't have lead water mains. We would have maybe iron water mains, plastic-based water mains, whether it's PVC or some material like PVC. Sometimes we have concrete-based, and sometimes we'd have ductile iron-based. Certainly there's a lot of cast iron-based systems, again, in the northeast parts of the country, simply because it was a material that was relatively cheap and effective to manufacture in the late 1800s.
Hi, my name is Lauren. I think you may have touched on what I'm asking about in this last question, but I was wondering if you know of any non-metal service pipes that are being used or could be used that may prevent some of these issues.
Yeah, hi, Lauren. Yeah, so most of the PVC is very common, or polyvinyl chloride is a very common plastic. There's other plasticizing agents that can be used. One of the challenges, I assume in Michigan, I grew up in Ontario, which is on the other side, fairly close to Michigan. We used to drive through Michigan quite a bit. We get snow in Ontario, you get snow in Michigan. One of the challenges with plastic-based pipe is just the strength of the pipe. Why we still rely on iron-based pipe is the strength of the material is very nice, particularly for colder climates, in that we tend not to, through freeze-thaw cycling, the material is a little more, has a stronger strength. Certainly, plastic pipe has come a long way, and that we can get better service life out of these pipes. But certainly, historically, that's been one of the challenges with some of the plastic pipes in water mains. In our homes, obviously, using plastic pipes is very common, and we really wouldn't worry about freeze-thaw cycles in our homes.
Okay, any other questions? All right, so we want to thank our speaker again.
Thank you.
Very good. So you are also our last guest speaker for this semester. From here on out, we're going to have our students presenting. So, yes.
Excellent.
I know. So next week, we should be hearing from Adriana, Noor, Ali, and Alistair. Okay? Thanks again.
Thank you.